Welcome to section 13.3. Today we're going to talk about systems of equations. I have tried to scale this back a little bit so that we're just doing some brief review of some ideas that we've talked about all year, and then kind of introducing a couple of new ideas, new topics that might be a little bit different but involve some circles or some other types of equations as well. So first, let's talk about solving systems of linear equations when we're graphing. Remember, if we had parallel lines, then there are no solutions because there's no intersections. We would either state no solutions or in our set notation put our circle with our slash through it, stating that it's the null set. Intersecting lines, it's always about the intersection, so there is only one solution in that case when they are lines, but we would put the ordered pair of the intersection, and as I look closely, I believe I did get that correct. If both equations graph the exact same line, or there is only one line, then there are infinitely many solutions, or there are all points on that line are solutions, and we would state it using set builder notation this way. The set of all ordered pairs x and y such that it forms this line, it meets this equation. That's the way to state that it's infinitely many solutions using set builder notation. And as we get into some of the practice problems here, for example 1, this is something like we've been using for all semester at least, and I'll kind of walk through using substitution in this case. But you could certainly use elimination in a problem like this. I'm just going to make sure that I use both methods in an example so we have access to both of them. But if I'm using substitution, I need to solve an equation for either x or y. And in this case, solving the first equation for x would probably be the easiest, because I could subtract 6y from both sides and get x equals negative 6y plus 1. Now I'm not using this equation, I'm just going to kind of put a little cross through it, but it's really just rewritten. Now I would substitute negative 6y plus 1 in for x in my second equation. So the second equation becomes 3 times the quantity of negative 6y plus 1 instead of 3x minus 10y equals 31. Go through, and through the magic of video, we get our y value to be negative 1. And more magic gives us x equals 7. So once we get the first variable, we have to substitute back into an original equation to find our second variable, write your answer as an ordered pair. There's one solution. Example 2 can look a little bit tricky when we have this fraction. Don't forget, it's often easier to clear a fraction before we start dealing with this. So when I talk about that, what I mean is, whoa, what happened there? Fixed it. All right. What I mean is I'm going to take this entire first equation and multiply everything by 2. That way when I distribute a 2 into here, 3 halves times 2, I get 3x. Distribute the 2 into here, I get minus 2y. Distribute the 2 into here, I get equals 6. That's clearing that fraction. And then I have 3x minus 2y equals 12. We'll fix that here in a moment. At this point, done. At this point, we don't eliminate yet, but I am going to use elimination here. So I personally like to get opposite coefficients. You could just look at this and say, well, I'm just subtracting, and you'd be right. There's not an issue with that. But personally, I like to take one of my equations and multiply it by a negative. In this case, I'll multiply this bottom equation by a negative 1, and that means I'm not changing the first equation. It's still 3x minus 2y equals 6. The bottom equation, though, becomes negative 3x plus 2y equals negative 12. That way, it's just easier visually for me to see that in elimination, my x's are lined up vertically, my y terms, my equal sign, and my constants are all lined up vertically. I can just add, combine my like terms straight down. But in that case, that eliminates, and that eliminates, and that does not eliminate over here. So I get 0 equals negative 6. Variables both eliminated, and I'm left with a statement that's not true. We know that's not true. That's the sign that we have no solution. These two would be parallel lines. If my variables both eliminated and my constant eliminated, now I have 0 equals 0. That's a statement that is true. That would be infinitely many solutions, or all points on that line. All right. Hopefully we're all caught up to speed on those. We are going to flip to the next page and start looking at example 3. Take a minute, read through it, and see if you can get started on what that might be asking us to do. So there is a lot going on in this problem, but first and foremost, they want me to write the equation of a line. So I need a point and I need a slope. My slope, because it's going to be perpendicular to the graph of this line, which has a slope of -2/5, the slope I will use is 5/2. The point I want to use needs to be the intersection of these graphs. That's a solve a system of equations problem. And since y is equal to x plus 3 and it's equal to -2x plus 21, then x plus 3 has to be equal to -2x plus 21. Running with that, we get our x value to be 6, plug it back into one of the equations to get our y value of 9. We now have our point and our slope. Like we talked about with 13.2, we'd probably want to write this in slope-intercept form. So I'd go ahead and calculate my b, and y is equal to 5/2 x minus 6. Now we get to some stuff that might be a little bit new, a little bit trickier. So pay close attention. We have the equation of a circle, x squared plus y squared equals 4, and the equation of a parabola, or in fact it's not a parabola because it's not x squared, but we have -x plus y squared equals 4. It's not a typo. This is not an x squared. In this case, again, I personally like to use elimination, so I can't eliminate x squared and x. They're not like terms. But I will be able to eliminate my y squareds if I either subtract my equations or if I multiply this bottom equation by -1, keeping my first equation as x squared plus y squared equals 4. My bottom equation becomes a positive x minus y squared equals -4. Now I can add my equations, but these are not like terms. Okay? Y squared minus y squared eliminates, and in fact, so does 4 minus 4. But I'm not going to just eliminate 4 minus 4 because that's the only thing on that side of my equal sign. That's going to equal 0. But the left side becomes x squared plus x. It's not an x squared. Now I have a quadratic that I have to solve. I can solve that any method we know with quadratics. This one is set up pretty well to solve by factoring. If I factor out my common factor of x, that leaves me with an x plus 1, that equals 0. It was already equal to 0, so I was in good shape there. That gives me two possible values for x. X could equal 0, or x plus 1 could equal 0, meaning x is equal to -1. Well, if I have two values for x, I have this option going on right now. I'm looking at my solutions. X could be 0, x could be -1. What are my y values? Well, let's look. If x is equal to 0, then I have x squared plus y squared equals 4. I have 0 squared plus y squared equals 4, or y squared equals 4. Solving by taking a square root, though, is going to give me two possible values for y, +2 or -2. So I actually have to go back over here. I could have the solution of 0, 2. I could also have a solution of 0, -2. And I still haven't looked to see what happens if x is equal to -1. So I had these two possibilities here. If x is equal to -1, then I have -1 quantity squared plus y squared equals 4. 1 plus y squared is 4. which means y squared is 3, or when I take the square root of both sides, y is equal to plus or minus the square root of 3. So once again, if x is -1, y could be the square root of 3, or the opposite of the square root of 3. Let me review that real quick here. We found two possible values for x, but each value of x had two possible values of y, meant we had four possible solutions to this, and that's because these are not just lines, so they could intersect in more than one place. These possibly actually do intersect at 4 different locations on the coordinate plane. With that in mind, see what you can come up with something like number 5. To start, we should see that we have two possible values of x. These were set up to use elimination immediately. And in this case, you wind up getting the same two possible values of y because these were a circle, and then x squared minus y squared is actually going to be a hyperbola, so something that we haven't studied yet. It'll probably be studied a lot more depth in Algebra 2, but it's a slightly different type of a shape. And the x coordinates are 4 or -4, but the y coordinates are 2√3 or -2√3, no matter which value of y or of x we select. All right, there's a few practice problems that we've assigned for homework. Go ahead and take a look at those and see what you guys can come up with that.